Georgia Tech, OMS, INTA 6450, Data Analytics and Security, Spring 2025, Term Project Presentation, Group 3, based on NowSecure. Group 3 team members: 1. Lakshmi Arti, 2. Jean-Marie Vaneskahian, 3. Keith Crow, and 4. Travis Carlisle. Each of the team members contributed equally to both the paper and this presentation. Overview. This term project presentation is based on a more comprehensive and detailed paper. The topic revolves around the NowSecure mobile application testing framework. Abstract. Our team has conducted a unique analysis of mobile app security. We studied JSON files from NowSecure. These files included detailed data about apps scanned for security issues. Each JSON file contains extensive information regarding various aspects of app behavior. We carefully extracted key metadata fields. Each of these fields included embedded FQDNs and URLs accessed by the apps. In addition to counting each occurrence, we interrogated each occurrence to find instances of connections to risky top-level domain and known trackers, specifically trackers connecting to third parties associated with data collection and data analytics services. All counts were then collected into a single spreadsheet. This CSV served as the foundation for our deeper analysis. After organizing the metadata, we created additional important metrics. We looked closely at sensitive permissions requested by each application. This included critical access rights needed on Android devices. Examples of sensitive permissions are access to location contacts and messaging services. Counts of these sensitive permissions were added to our spreadsheet. Each app was clearly marked based on these counts. This provided an easy way to identify apps that requested unnecessary sensitive data. It also enabled us to see common patterns across multiple apps. Finally, we applied advanced machine learning and Python code with an isolation forest algorithm to our data. An isolation forest is effective at detecting outliers by isolating anomalies and allows us to spot unusual patterns in our dataset. The algorithm clearly revealed anomalies and outliers. These results highlighted risky behaviors overlooked by standard NowSecure reports. Our approach provided a broader view by analyzing apps together instead of individually. By considering multiple applications at once, we discovered broader security trends. Our findings offer valuable insights into common vulnerabilities affecting mobile apps today. Raw data. NowSecure static and dynamic tests. The NowSecure testing and assessment framework incorporate both static and dynamic analysis. We used the OWASP risk categories to guide us in our effort to identify static test case results that we wanted to focus and ultimately collected for analysis. NowSecure CVSS finding tests. NowSecure test reports provide results across many test categories. NowSecure overprivilege checks. Part of the important data that NowSecure provides was overprivilege check. This helped us in generating new metrics based on these checks. NowSecure dynamic network connections. In addition to static analysis, we leveraged results from the dynamic analysis section of the reports. We wanted to collect and measure instances of leaked logcat data as well as dynamic network connections to hosts associated with risky third-party SDKs. Samples of the individual results we focused on can be seen here. Spamhaus risky top-level domains. We used domain reputation data provided by Spamhaus to build a list of risky TLDs. We recognize that the approach is not perfect, and simply connecting to a risky TLD does not necessarily infer malice. We believe it's a useful measure to consider alongside other indicators of possible privacy invasions. Risky analytics trackers. We leveraged Exodus Privacy to identify known trackers, specifically trackers associated with firms that specialize in location detection, profiling, identification, and analytics. According to their website, Exodus Privacy is a, quote, nonprofit organization led by hacktivists. Its purpose is to help people get better understanding of the Android application's tracking issues. They define a tracker as a piece of software whose task is to gather information on the person using the application and how they use it, or on the smartphone being used, close quote. Putting it into code. Step-by-step execution. In order to determine outliers in the aggregated feature set, the team used Python and various Python libraries in the following way. First, the proper libraries and modules were imported. This included pandas for data wrangling, sklearn ensemble for isolation forest, sklearn preprocessing for standard scalar, and finally, Seaborn for graphing. Modules and libraries imported into Python. Here's a screenshot of the various aforementioned modules that are called by the Python code. Python coding risky permissions. Here we encoded the risky permissions into the Python code to help generate the consolidated spreadsheet. Python list containing risky trackers. With information provided by the Exodus Privacy, we attempted to identify specific trackers and build metrics around instances found in the NowSecure reports seen in the figure of our Python code here. Python lists containing risky top-level domains. The top-level domains were deemed risky, and top-level domains decided to identify and measure are seen here within the Python code. Data processing methodology. Python snippet of CVSS results processing. Using NowSecure reports as our initial dataset, we build a Python script to parse and collect metrics for inclusion into a comma-separated table that could be subsequently processed for patterns. We were provided with a set of 84 JSON formatted files included of the total 185 individual NowSecure mobile app scan reports. After normalizing the set of reports, our final CSV contained data from 147 individual reports. After identifying the individual test results that we wanted to measure, our fundamental approach was to simply count the occurrences across the mobile app scan report. An example can be seen in the figure, where we count not only the number of CVSS findings as a whole, but also count the high and medium impact CVSSs. We believe that high and medium impact findings are a sign of poor security development lifecycle practices or can possess risk to the user's privacy. Python snippet of processing app permissions. There were other test results that require further processing and filtering before establishing the final metric, such as checking for overprivileged applications. Python snippet of processing URLs and FQDNs. Here we identify the connections to the risky top-level domains and data collectors. Python snippet of processing metrics into CSV files. After measuring occurrences of the test results we were interested in, we appended them into a CSV file. That included metrics of all the mobile apps under test. Proposed strategies, analytical tools, and techniques. The team discussed various strategies for the project, from the use of classification machine learning algorithms to various linear regression algorithms to determine malicious mobile applications. After reviewing various options and discussing the pros and cons, the team decided to do a two-prong approach where we decisively picked specific features in the NowSecure data and then use them to feed into a machine learning algorithm to determine potential malicious applications. The solution leveraged the team's security experience to help with the feature selection and leverage the team's machine learning knowledge. Once the path was solidified, the team then had to determine what machine learning algorithm would be best fit to assist with the determining potential malicious applications. One of the challenges was that the team did not know if the applications were determined to be malicious or not by NowSecure. This meant that the data could not be used to train the model for classification, i.e. supervised learning. After some research into potential solutions, the team decided to use isolation forests, as it can be used to determine outliers in the dataset, which could point to potential malicious activity and thus malicious applications. Analytical tools and techniques for the analysis the team looked into using R and/or Python initially, but based on the research that the team did, it was determined that Python and Python libraries could do everything that was needed. The team mainly used pandas to do the data wrangling, which consisted of viewing the data, checking the data type for each feature, checking the statistics on the data, count, mean, min, max, etc., looking for any missing or empty values, splitting the application names from the data, normalizing the data, and finally concatenating the data. For the machine learning algorithm and determining the applications with outliers in their datasets, the team used the isolation forest library from scikit-learn module. The standard scalar library from scikit-learn was used to normalize the data. In order to plot the data and get a better understanding of the outliers, the team used the Seaborn module. Implementation. CSV data import and review. The team imported the processed data and reviewed it. The team used various Panda functions to display information on the data, describe the data, review the first few rows of the data, and check for missing data fields. Data description. This gave us a statistical breakdown of each of the important fields. Data review of the first few rows. When we did an analysis of the first few rows of the data to better understand what we needed to clean up next, this gave us a baseline of what data fields needed to be modified. Check for null data. This was a check for the fields that had no data associated with them. Check for NA data. Checks were performed on the NA data that existed in the dataset. Checked for data converted to numerical values. This included forcing features to be numerical values, scaling the data, and then converting it back into the data frame before any machine learning was done on the data. Data split and reviewed. After reviewing the data, the team split the data so further analysis could be done on the features. Here is code that goes over that process. Data scaled and isolation forest used for outlier analysis. With the data cleaned and normalized, the team used the isolation forest module to find outliers in the data. New columns were created to denote which applications were determined to be anomalous and which ones were not, and to denote what their scores was. This negative score indicated outliers and positive scores indicated normal behavior. Final review after anomaly analysis. The data is then concatenated with the first row and new columns, and applications noted as anomalous were then printed out along with a designation and anomaly score. Again, the negative scores point to possible malicious applications, whereas positive scores denote applications that are under normal behavior. Checking numbers of potentially malicious apps against all apps. After the malicious applications are listed out, the team then used the Seaborn module to display the data for further visual analysis. This was used as a sanity check to validate that anomalous applications were in fact the minority of all the applications scanned, which was borne out by this graphical representation. Challenges and solutions. Several of the challenges the team faced were on the implementation of the machine learning model. The team experienced several errors when trying to normalize the data. To troubleshoot this issue, the team used data.info to check data types, and it was found that the features had the data type of object instead of integer data types. After this was found, the team went into the spreadsheet and did further analysis of the data and found that some of the data fields contained the word none. The team looked at various solutions to help normalize or determine what value to place in the fields, but ended up just dropping that data, as overwriting it with another value would poison the integrity of the data. After the data was cleaned up and converted to an integer, the normalization was rerun and the data was normalized without issues. Results. Mobile applications determined to be potentially malicious. Data analysis and findings. After data analysis was done, it was determined that the following mobile applications had values that were outliers and should be investigated for malicious activity and privacy violations. Interpretation of the results. The mobile applications that were determined to be malicious still need further analysis to determine if the data outliers lead to malicious activity or privacy violations. The team's recommendation would be to use this list of potentially malicious mobile applications to further analyze applications using security tools. If the results do not lead to assisting with a new way to identify malicious mobile applications, then the feature selection process may need to be reworked, or the isolation force parameters may need to be modified such that the outlier selection is refined. Discussion. Evaluation of the approach. Our chosen methodology matched our initial research goals. We set out to clearly detect hidden privacy risks in mobile applications. The chosen metrics and features proved effective for this goal. Using sensitive permissions, counts, and DNS domain metrics directly addresses our objectives. We anticipated that our analysis might reveal broad patterns. The actual findings strongly support these expectations. Our machine learning approach successfully identified outlier applications which should correlate with security concerns that will require further analysis to confirm. Depending on the results of this analysis, the feature and model parameters can further be adjusted to improve malicious activity detection and privacy violations. Overall, our methodology highlighted several key vulnerabilities. It demonstrated the effectiveness of a holistic approach in analyzing app security data. This approach significantly improves upon single app analysis methods and gives us security teams a powerful tool to address complex security issues. Conclusion. Summary of findings. Our findings confirmed what we set out to prove. Many mobile applications request access to sensitive data. Some do this without clear need. These requests often overlap with known tracker connections. That combination possesses a serious privacy risk. We discovered apps that contacted risky top-level domains that were flagged by threat intelligence sources. That means that they are often linked to spam, malware, or other shady behavior. We also found apps using trackers associated with profiling and advertising. This behavior may go unnoticed during basic app reviews. Using an isolation forest, we found clusters of anomalies. These were not visible from the basic counts alone. Outlier apps had higher permission counts. They accessed more sensitive fields and contacted more suspicious domains. They were not just technical findings. They were real indicators of risk which need further investigation and analysis. This approach showed privacy risks can be measured. The data speaks for itself as several apps show clear deviations around privacy. Our results showed that anomaly detection gives useful insights beyond traditional security scans and can be used to identify potentially malicious mobile applications. Implications and recommendations. The broader implications are clear. Users download apps every day. Most never read the permissions. Most never check the domains an app contacts. These behaviors need oversight. Our work suggests a new way to get that oversight. Security teams can use our methods to filter out high-risk apps. App stores can rank apps based on these anomaly scores. Developers can be encouraged to avoid excessive permissions. Policies can be built on actual data patterns. We recommend that developers follow principles of least privilege. Only ask for permissions that are truly needed. Avoid embedding third-party SDKs that collect user data. Use static and dynamic testing to detect data leaks. We also recommend further research and testing. Expanding the dataset, adding known malicious samples, trying new models like clustering and learning, even mapping anomalies to known attack patterns are all potential options that should be investigated. Each step should bring more precision. Our work is a step towards data-driven mobile security. It shows the value of combining domain knowledge and automation with advanced tools like machine learning. This combination makes privacy risk visible, and that visibility leads to better protection for users. The end. We hope you've gained insightful knowledge and also enjoyed the presentation as much as our team enjoyed doing the research and putting it all together for you.